percentage, percent recovery, membrane fouling, and concentration polarization. Explain osmosis, reverse osmosis, dialysis, electrolysis processes, and how they differ from each other. And the last one will be, it will enumerate some of the important application based on membrane separation from different rates of science and technology. So these things we will have a broad or basic knowledge on these parts, like uh, the different aspects and importance of membrane process. It will also involve what are the membrane based separation, what is flux, solute retention percentage, percent recovery, membrane fouling, and concentration polarization. Then we have mechanism of osmosis, reverse osmosis, dialysis, and electrolysis. And the last one with the general application. So we have these things now. That is, before you go to the mechanism process, let's have a general idea on your membrane separation. So just uh, look at this figure, where the middle arrow line in this cubical structure, or it is the container of the the sample, it is the membrane. Okay, so this is the membrane. Generally, it is the semi-permeable membrane which allow the solvent particle to pass through it and leave all the solute particles. Then influent with substances A and B, and these are the permeate depleted with either A or B. So these are the two zones, and this is the concentration enriched with either A or B. The A or B are the two components in the mixture. In membrane separation, two bulk processes are separated by a barrier which is called the membrane. The membrane controls the passage of different chemical substance through it, which depends upon the nature of the chemical substance and the membrane. This results in depletion of that substance in the permeate through the membrane. So various factors which govern the process of membrane separation, like your permeation through the membrane, which type of membrane you are using, what type of solution is under separation. So these things are very much important. The membrane phase can either be non-porous, microporous, mesoporous, or macroporous. By classification, if the pore size is between 20 angstrom to 500 angstrom, then it is mesoporous. And pore size larger than 500 angstrom is macropores. A membrane can also either be a solid or liquid. It can be polymeric material, inorganic refractory compound, or a metal or their composites. So these are the different classification of your membrane, that is non-porous, microporous, mesoporous, and macroporous. If it is less than 20 angstrom, the pore size, it is microporous, and if it is non-porous means there will be very minute number of pores, or there is non-availability of pore is there in the membrane. So we have again our, yes, this one. So the general aspect of membrane process, we've already discussed that one, that is general aspect. And another one mathematical term is there, that is the performance of the membrane is defined as the, in terms of two parameters, that is transmembrane flux and solute retention or solute selectivity. So just go to the PDF again. Just wait. Yes. So there are two simple parameters which govern the membrane performance, that is transmembrane flux and solute retention or solute selectivity. So transmembrane flux is the permeation rate, that is uh, the flow rate, or it is the kinetic flow rate of the components, different components of a mixture through the membrane. It is known as permeation rate. Uh, is the volumetric or mass or molar flow rate of the fluid passing through unit area of the membrane surface per unit time. So this is the known as the transmembrane flux. So it is the rate at which the volume or mass or molar flow rate of the fluid passing through unit area of the membrane surface per unit time. So the transmembrane flux of any species is directly proportional to driving force, and a driving force applied across the membrane and is inversely proportional to the effective thickness of the membrane. So if the thickness is more, the transmembrane flux will be less. So this is inversely proportional, and it is directly proportional to the flux or the force at which it is applied. If the driving force is described in terms of hydrostatic pressure gradient P or partial pressure difference delta P1, Pi, and concentration difference delta Ci across the membrane. So this concentration difference is before the separation and after the separation difference. So then the transmembrane flux J of ith species is equal to Pi followed by your del Pi, that is the total pressure gradient, or partial pressure gradient delta Pi small p, or delta Ci, it is the concentration difference divided by delta, where Ji is the transfer flux for species I, Pi is the permeability of species I through the membrane, and it is effective membrane thickness, that is delta. The ratio of permeability of process species I to effective membrane thickness is sometimes called permeance. So the
Hi,
permeability of the
madam.
species through the membrane with a definite thickness is also known as permeance. The retention or selectivity is a measure of the relative permeation rates of different components through the membrane. It is known as the retention or selectivity of the membrane. It is also expressed in terms of selectivity coefficient alpha. So for species A and B, alpha will be Pa by Pb. It is a permeation of A divided by permeation of Eb. This will be the selectivity coefficient. The selectivity coefficient also can be expressed in terms of concentration, that is selective coefficient alpha of AB equal to concentration of A by concentration of B divided by concentration A by concentration of B. It is C. So C and CB represent the concentration of AB respectively, and P and C represent, that is the permeation and concentration terms. So this is permeation divided by C and CB at different concentration. Some important membrane processes, it will include separation objective, the nature of the substance which need to be separated from the nature of the mixture, the nature of the species retained by the membrane, the nature of the species permeating through the membrane, the driving force needed to achieve the desired separation, the mechanism of separation. So these are the different factors which govern the process of membrane separation. Then that include your nature of the substance to be separate, undergo separation, nature of the membrane, nature of the species permeating through the membrane, and it's the force and the type of separation mechanism. So reverse osmosis, this is a common phenomenon which is very much familiar with us, as we know in different water purifiers. like your aquaguard, canned purifier system, or any other water purifying system, you may you might see uh, this RO is written over that machine, water purifier machine, RO. So this RO stands for the reverse osmosis. So in reverse osmosis, what happened? Just see this one. Yes, this one. This is known as reverse osmosis. What happened in this process? We will have a membrane here. This membrane is your semi-permeable membrane, SPM. So this semi-permeable membrane allows the solvent particle flows through it. The solvent particle pass through it, behind remaining, or it will left or separate. It is a separation of the impurities present in the water in the left side, and pure water or trace water will be separating at the right hand side. So this is known as the reverse osmosis process, which allows only the solvent particle from the solution, and it gets separated through a semi-permeable membrane. This is your mechanism of your water purifier, that is your RO. So we have then we have this type of things are there, and that is the hydrostatic pressure is applied up to 2 MPa to around 6 MPa, then a size of less than 10 angstrom, uh, where reverse osmosis process is used, and that is weight less than 300. It is also applicable. This is a schematic diagram, that is semi-permeable membrane. This is the solution or the impure water, and only the solvent particles are allowed. So we will get pure water through this mechanism. Then we are followed by nanofiltration. Nanofiltration means if the pore size of the membrane is around 10 to 30 angstrom, then nanofiltration will be carried out, and which is followed by your ultrafiltration. In ultrafiltration, we have pore size of 30 angstrom to 200 angstrom. This is our ultrafiltration range, which in which 500 kPa of the force or pressure is applied. So this is your ultrafiltration. Okay, where the pore size is 30 angstrom to 200 angstrom. Then it is followed by microfiltration, where the sub micron size, that is less than zero point 0.1 micrometer of particulate matter from the solution. This process is also requires hydrostatic pressure gradient across the membrane. The pressure used here is 100 kPa or so. The pore size of the membrane decides the size of the particulate matter retained. The process is similar to ultrafiltration, and separation takes place by sieving. Sieving is just the filtration with the help of your some filtering materials. The essential difference between ultrafiltration and microfiltration is the size of the macrosolute retained, pore size of the membrane, and the hydrostatic pressure needed across the membrane. Typical application of microfiltration process are in the removal of bacteria from water sample, and removal of submicron size suspended dust and particulate matters from gas streams. A removal of chemical oxygen demand, CO2, from effluent water is another important application of your microfiltration. So this is different type of filtrations or membrane separation processes. I am showing my, yes. So let's have some PPTs. This is microfiltration, where where the membrane is here with your 30 angstrom to 200 angstrom. It is the pore size, and these are the samples here. And then with the application of external pressure, this will be permeate. Okay, so this will be separate. This is microfiltration. Then the retented by the recirculated to the feed, a dynamic membrane may be created by adding lime or potassium permanganate to the feed to precipitate manganese oxide on membrane. So this is another just one example of your microfiltration. Then it is your feed, uh, that is the suspended solid or colloids or dissolved solids, which undergoes your membrane operation. That is let it be 100%. Then suspended solid is separated. That is the 50%, and the low molecular weight dissolved solid separated is the 50%. So in this membrane, through this membrane, uh, this type of separation also carried out. This is to reverse wear reusable things. Application of membrane wastewater treatment, pressure driven solid liquid separation process, tertiary treatment of wastewater following secondary sedimentation, production of high quality effluent in reuse schemes, alternative to sedimentation tank for solid liquid separation. It is maybe anaerobic or aerobic biological technique. So this is another example of your, it is your micro filtration, where this micro filtration done here. Okay, that is aerobic biological process. This sample is gets filtered with this micro filtration membrane, and this is secondary sludge, and this is the final effluent with some biological oxygen demand and suspended solid SS. This is an anaerobic reactor where the use of ultrafiltration or microfiltration unit is here. The sample gets separated through this membrane as the effluents are separated here. Then we have what are the advantages. They are usually continuous, comparatively low energy utilization, no phase change of contaminants, small temperature change, modular design, minimum of moving parts, and physical separation of contaminants will also there in your in these advantages of membrane processes. Then this is just a distinctive presentation of your different type of membrane separation processes. We have reverse osmosis. It is in the range of 0 to 100, followed by nanofiltration. In nanofiltration, we have two types: micromolecular filtration and macromolecular. So the total range 0.001 to 0.01, or it is 200 to 20,000. Then we have microorganisms undergo ultrafiltration, that is 1 lakh, and if it is coarse particle, that is the smallest one, that will be 5 lakhs, or it is 0.1 micron. So depending upon the pore size, we have different type of membrane separation processes, and on the basis of that, we will choose a different type of membrane separation processes depending upon the size of the particle to be separated. This is the applied pressure. Reverse osmosis, this is 100 to 800 psi. Ultrafiltration 5 to 100 psi, and for microfiltration it is very low. Microfiltration design consideration: it is high flux, back flushable, high membrane area or volume ratio, allowing low pressure drop while maintaining high tangential velocities, simple installation and continuous operation with minimum supervision, low operating pressure, easy maintenance and simple membrane replacement, low energy consumption, and the last one will relatively low capital cost. So these are the things. Then we will go for another important part. We'll go for another important part, that is the dialysis. This is the dialysis part. This is another important separation process involved in your membrane separation method. So what is dialysis? Let's have this one. The dialysis membrane is, this is another membrane. Okay, the dialysis membrane. This dialysis membrane is thin with micropore size such that solute of type A can pass through by a concentration driven force. Solute of type B, so this is solute of type A, which is passed through by a concentration driving force. Solution of type B are larger in molecular size than those of A and pass through the membrane only with difficulty or not all. That means the solution in solution B, the particle size is larger than solution A. So particle B or solution B particles will penetrate or permeate through this dialysis membrane very slowly, and it is followed by colloids blocked by the membranes, do not pass through this membrane due to large size. So here we have osmosis, where there is flow of the solvent particle through this dialysis membrane. Solution A with a definite size pass through the membrane, but solution B with a larger size, thus the flow is very slow, that is slow dialysis, and collides with larger size particles will not pass through these things. So when P1 equal to P2, that means pressure at the left side and pressure at the right side. This is just equal to both. The solvent may also pass through the membrane, but by a concentration driven force acting in the opposite direction, that is osmosis. So in osmosis, there is the force is acting on the opposite side of the flow of the solvent to stop osmosis. This is also known as osmotic pressure. When P1 greater than P2, solvent osmosis can be reduced or eliminated if the difference is higher than the osmotic pressure. If the pressure on the left side is greater than pressure on the right side, then at that point then what happened? This pressure will be greater than your osmotic pressure. If it is greater than osmotic pressure, then the osmosis process may be stopped or the flow will be reduced. Then the third one, diffusate, where the solvent solute of type A and a little or none of the type B solute. Then dialysis, solvent B solute remaining type A solute and colloid material. So in dialysis process, these solution B type components are separated through your dialysis process. So dialysis is attractive when concentration difference for the main diffusing solute are large and permeability difference between these solutes and other solutes or colloid are large. What are the applications? So just remember these things. The solution B and colloid type materials can be separated through this dialysis process. What are the application? A recovery of sodium hydroxide from a 17 to 20 weight% caustic viscous liquor containing contaminated with hemicellulose to produce a diffusate of 9 to 10 weight percentage of caustic, recovery of chromic, hydrochloric, and hydrofluoric acid from contaminating metal ions, a recovery of sulfuric acid from aqueous solution containing nickel sulfate, a removal of alcohol from beer to produce a low alcohol beer, a recovery of nitric and hydrofluoric acid from spent stainless steel pickle liquor, removal of mineral acids from organic compounds, removal of mineral low molecular weight contaminants from polymers, purification of pharmaceuticals. So these are the some applications of your dialysis process. And also dialysis process is very much a your in the medical that is in the health treatment. This process is also uh, an unique process, a unique method of separation of your urea, creatine, uric acid, phosphates. Like it is known as a hemodialysis, where the where the blood gets blood a new blood is replaced by um, the contaminated bloods. That is removed from the blood without removing essential higher molecular weight compounds and blood cells in a device called an artificial kidney. Okay, so this type of medical treatments also this dialysis process is very much important. We have some mathematical equations for this. Dialysis membrane can be thin because pressure on either side of the membrane is essentially equal. That is P1 equal to P2. Differential rate of solute membrane transfer across the membrane, that is dNi equal to Ki CIF minus CIP, differential of Am 1 by Ki equal to 1 by KIF plus Lm by Pmi plus 1 by KIP. That where Ki is the overall mass transfer coefficient. This is Ki, overall mass transfer coefficient. Water transport number, the ratio, it is a ratio of the water flux to solute flux with a negative value indicating transport of solvent in the solute direction. So this is the transport number of water. Transport number of water means water gets mm, transport from solvent to solute side. So this is the transport number. The most common dialysis membrane module are plate and frame and hollow fiber. In a plate and frame dialyzer, the flow pattern is nearly counter current when total flow rate changes, little and solute concentration are small. And there is another equation is there, Ni equal to Ki Am delta Ci Lm, where this concentration of the Lm, that is Lm stands for a log mean concentration driving force. Just try to remember these mathematical terms related to dialysis. Then followed by electrodialysis, another important membrane separating process, which involve your electrodialysis process ED. So electrolytic dialysis process, it is for separating an aqueous electrolyte feed to feed into concentration and dilute or desalted water diluted by an electric field and an selective membrane. So here what happened? Electric field is applied and the ions get separated. Ions get separated by the applied electric field. Cation selective membrane carry a negative charge and attract and pass oppositely charged ion cations, while retarding negative ion or anion. It is just similar to the ion exchange chromatography, where the cation exchanger will carry the negative ion and anion exchanger will carry the positive ion. In the similar manner, in electrodialysis, the cation selective membrane, these membranes having some charges. This is C is your negative, A is your positive. So A is the anode type and C is the cathode type. So this negative membrane will mm, will carry the positive ion, and the positive membrane will carry the negative ion. This is just vice versa. So this is anion selective membrane carrying a positive charge that attracts and permits passage of anion and vice versa. Both type of membrane are impervious to water because water is very much neutral and compartment pressure are essentially equal. So this is undergoes your electrodialysis where application of electricity is there and the membranes carry either positive or negative charge, that is cation selective or anion selective membranes. Then we have then we have the next one, that is the electrodialysis next part, that is water the separation of water to hydrogen and oxygen. Both the electrodes are chemically neutral metals, with the anode being typically stainless steel and the cathode platinum coated tantalum, niobium, or titanium. So, for the dialysis, electrodialysis of water, the anode used is the stainless steel, and the cathode is it is the niobium, titanium, or tantalum metal. The most easily oxidized species is oxidized at anode, and the most easily reduced species reduced as cathode. So oxidation means it is the removal of electron, whereas reduction means it is the gain of electron. So at the reduced end, that is at the cathode, what happens? There is release of hydrogen gas H2. So water molecule accept electron and will form hydrogen gas with the two hydroxy groups, 2OH minus. Here the standard reduction potential is minus 0.828 volt. So this is the amount of electrical energy generated through this reductive half cell reaction. Similarly, at the anode, what happen? Oxidation will happen. Oxidation is release of electron or loss of electron. So water loses two electron to produce oxygen gas with liberation of 2s plus. So here what happen? In the medium, both OH minus and S plus are there. So again, the water molecule is regenerated, and here the standard reduction potential is minus 1.23 volt. So the overall reaction will be 2 water and water, 3 water. These two electron gets cancelled. So we have H2 half O2 2H plus plus 2OH minus. So this 2H plus and 2O minus, this will be again water. So we have the net reaction is water give rise to H2 plus half O. So this will be the net reaction of this process, and the total uh, E0 reduction, that is the standard reduction potential will be minus 0.828 volt minus of minus 1.23 volt. Just calculate the value and we will get the amount of EMF generated through electrodialysis of water. Very simple. The reduction happen here, so hydrogen is removed. Oxidation happen here, so oxygen is removed, and here electron is gain of electron. Here loss of electron, and at the end we have the net cell reaction or net reaction. Then this is the electrodialysis instrument where uh, this is just a membrane, that is the anodic membrane with negative charges, and there will be positive charges or cations will be attached here. So a cell pair or unit cell contain one cation selective membrane and one anion selective membrane. This is become a cell pair where a cation and anion with equal number are present, A commercial electrolysis system consists of a large stack of membranes in a plate and frame configuration containing 100 to 600 cell pairs. Then in the stack, membrane of 0.4 to 1.5 meter square surface area are separated by 0.5 to 2 millimeter with special gadgets as the current density that is current in amps flow through the stack per unit surface area or membrane is increased for given membrane surface area. The concentration polarization effect increases. The maximum or limiting current density occurs when the CMD, that is concentration polarization density, reaches zero. So this is all about your electrodialysis process. We have some equations, that is the membrane area AM is equal to FQ delta C by I into epsilon, where F is the Faraday constant, Q is the volumetric flow rate of the diluate, delta C is the difference in concentration, then I is the current density of the cell pair, and epsilon is the current efficiency. Then power consumption P equal to I into E, that is ampere into voltage. Then electric current we have I equal to F2 delta C by N epsilon. That is the main application of electrolysis is to desalinization of brackish water in the salt concentration range of 500 to 5000 parts per million, that is milligram per liter. So this is one application of electrolysis to desalinitize the brackish water. Then we have reverse osmosis. This is already discussed. Then I just read these things. A dense membrane such as acetic or aromatic polyamide acts as semipermeable membrane. It's reverse osmosis. And we have asymmetric or thin wall composite membrane having a thin dense skin or layer or thick porous support are needed. And here the pH is maintained 4.5 to 7.5, and also polyamides are not susceptible to biological attack and resist hydrolysis in the pH range of 4 to 11. And just I will share this all pictures in your today in your WhatsApp group. Just go through these things. Then we have these mathematical equations of your reverse osmosis, where separation of solvent particles from a solution is through a semi-permeable membrane is happen. So these are the mathematical equations. Then we have the next part. We have already discussed these things. This is the anodic electrode, cathodic electrode. Then on the basis of the charge, different ions will be migrated. Then there will be gas separation also through your membrane, through some selective membranes. Then we have pore vaporization. There is one membrane known as pore vaporization membrane. Separation process where a membrane separates liquid feed and vapor permeate phases. So this involves pore vaporization through a specially designed membrane. Such some of the components in the liquid feed phase vaporizes and permeate through the membrane, and separation involve a phase change. Okay, this is the phase change from liquid to vapor. So this is pore vaporization. Then liquid membrane process is there, where liquids gets separated through through a membrane that is known as liquid membrane. And this process, the mechanism involved in separation using liquid membrane is it is very much simply a barrier between two phases, and if one component of the mixture move through the membrane faster than the other, separation is accomplished. That means here the liquid samples get separated through this membrane depending upon the movement of the separating particles of the respective constituents or components of the mixture. Different solutes will have different solubilities and diffusion coefficient in a liquid. As we know, this is known as the permeability coefficient. That is how fast or how the different particles gets passed through this membrane depends upon the permeability coefficient. So liquid membrane are encountered in three basic configuration: bulk liquid membrane (BLM). These are relatively thick layers, and another one type, that is the known as the immobilized or supported liquid membrane (ILM or SLM). It is the second category where microporous type membranes are there. And the last one is the immersion liquid membrane ELM, where it is also known as liquid surfactant membrane. And this is the third type of membrane under your liquid membrane separation. This is transport number or transport in supported liquid membrane, co-transport, coupled transport. This is the ion which having the negative ion, a counter ion NX minus. This C is the membrane. What happened? The CMXN membrane will form. So this is the synthesis of the membrane. So this membrane will stripping to membrane plus this one. So this gets separated. The membrane is separated and the ions get separated on the basis of their different sizes. So this is another example, that is the Mn plus is NHC membrane. We have MCN, that is M attached with the membrane plus removal of H plus ion. Then again these two will form, the membrane is separated and this will form H plus and Mn plus. Similarly these things happen and the equilibrium constant will be, and for this reaction there will be the concentration of the product, that is concentration of MCH-2 plus H plus square. This will be square here 2 divided by HC membrane square into M2 plus. This is the equilibrium concentration, that is concentration of the product divided by concentration of the reactant will be the equilibrium concentration. So this is the feed phase, membrane phase reaction, and at the receiver end, the separation will be done here, depending upon the particle size. Then we have this is the transport mechanism. This is the and B is the counter transport. This is the counter transport where the M plus and M plus is just imbibed into the membrane, and H plus is just get out of the membrane. So this is known as the counter transport. Mechanism of separation through sieving, already discussed. Solution diffusion. So this is depend upon the different diffusion process of the solution, how it is gets diffused in the solution, different constituents, and depending upon the same appreciable size difference, the separation will occur. Then we have preferential sorption or capillary flow. The sorption, I already told you that it is just the just both adsorption and desorption phenomenon will occur. This is known as sorption. So preferential sorption capillary flow mechanism was the fundamental approach for the practical development of arrow process for converting seawater into potable water. So this is just a mechanism. This is very much related to your RO, reverse osmosis process, where seawater gets converted to drinkable or potable water. If the surface of the membrane in contact with solution is of such a chemical nature that it has preferential sorption for water or preferential repulsion for solutes, then a multimolecular layer of preferentially sorbed pure water could exist at the membrane surface. So We have concept like critical pore diameter, and we have concept this is very much required for your separation of the seawater into pure water. Then we have Donan effect. So ion selective membranes show selective permeability towards ions of a particular sign. So this depends upon the ion selective membrane, that is just related to your just like your electrodialysis, where the membrane having some charges, that is cation exchanger or anion exchanger. The ion exchanger in the seat form a cation exchanger being selectively permeable towards cation, and anion exchange showing the same behavior towards anion. So the chemical structure of ionic exchange membrane consists of a network of carbon atom and styrene nuclei with a suitable functional group attached to styrene nuclei. If the membrane is immersed in an aqueous membrane, it absorbs water and swells due to the affinity between the functional groups and water. The functional groups dissociate to yield an electrically charged fixed group chemically bound to the hydrocarbon matrix, and a mobile ion carrying the opposite charge will happen. So in Donan effect, this is just a this is a synonymous with pure ion exchange mechanism, that it contain both cation exchanger and anion exchanger type membranes. So then we have some flow like Knudsen flow. So it is one of the possible mechanisms cited to explain the gas separation through membranes in the mean free path. This is to explain the gas separation through membrane. When the mean free path of the gas molecule is small compared to the pore size of the membrane, the formation of gas molecule is governed by viscous flow or hydrodynamic flow. So, the separation of different gas molecules through a membrane depend upon the it is depend upon the pore size of the membrane and formation of the gas molecule. The flow rate of the gas molecule is in viscous flow entirely proportional to pressure gradient causing the flow. So, uh, this type of Knudsen flow is important factor for the separation of gas samples or gas separation through membrane. We have surface flow, that means it is formation rate of a gaseous molecule through the membrane by enhanced, maybe enhanced in some cases by surface diffusion mechanism, where the gas is gets adsorbed on the surface of the adsorbent through diffusion process. In surface diffusion, gas molecule adsorbed. Here it is written, the gas molecule gets adsorbed to the surface of the adsorbate, that is the membrane, and then diffuse along the pore walls. Highly selectivity can be achieved in cases where preferential adsorption of the one of the component occur. So in surface flow, the surface is of the membrane where the gaseous molecule gets adsorbed on the surface to have the separation. We have facilitate diffusion transport. So facilitate diffusion transport, here a sample diffusion process is coupled with chemical reaction. So here diffusion occurs with some chemical reaction, and the net permeation rate may be greatly affected. Such a diffusional permeation is called facilitated diffusional transport. Facilitated diffusion occurs in a liquid membrane system. This mechanism requires a carrier substance X inside the membrane, which shuttle back and forth between the two sides of the membrane, carrying the permeant molecule A. The schematic diagram is just like this. That is from this end, the separation is supposed to be happen. This is the membrane, where at one end the A gets gets react with X to give AX, and AX at the other end, AX gets dissociated to give the A and X. So this gets separated. And in this process, separation occur by diffusion followed by some chemical reactions. Then active transport, this is by enzymatic transport, where there is enzyme is used. That's A plus in presence of enzyme, it will convert it to AB. Then at the other end, AB gets converted to A plus, and the separation occurs. So this active transport, active means it is active enzyme, and this is very much applicable to biological processes. Then osmotic phenomena or osmosis, this is already discussed. Then in osmosis, what happen? There is movement of solvent particles from solvent to solution site. So here, that is from a lower concentration to a higher concentration. The movement of the solvent particle, it is known as osmosis. If this process gets reversed, this is known as reverse osmosis, where the movement of solvent particle occurs from higher concentration to lower concentration. That is from solution side to solvent side, and through a semi-permeable membrane. And pressure when I applied pressure at the solution side to stop osmosis, it is known as osmotic pressure pi. So these are the basic concept. We have already learned this at our in our class 11, 12 or degree level. So these are very much common. Then we have some equations here: mu I zero equal to mu I plus delta mu I, where mu is the chemical potential. Chemical potential is defined as the change in free energy with change in number of mole at constant temperature, pressure, and other components. So this dg, it is change in free energy. So what is free energy? It is the energy of this of a system which when the value of dg decreases, the reaction is likely to be spontaneous or feasible. That means the decrease in energy responsible to make a reaction feasible or spontaneous, it is called as free energy. So in thermodynamics, we have a relation that is Gibbs free energy. So that's why this is written as dg. G stands for your Gibbs, the scientist Gibbs. So that's why G. So G is the free energy. So dg equal to sdt plus bdp, where S is the entropy of the system, that is randomness. T is the temperature, that is difference in temperature. V is the volume, and P is the difference in pressure. And here mu I is the chemical potential of ith species, and Ni is the number of moles of the component I. So this is a thermodynamic expression, that is dg equal to sdt plus vdp plus summation of mu I dni. Then we have, as I already told you, that chemical potential is change in free energy by change in number of moles at constant temperature, pressure, and other components. So from this equation, V equal to, what will be the equation for V at constant temperature? For constant at constant temperature, the T becomes 0. So STT is 0 now. So V equal to dG by dP at constant temperature. So dG by dP at constant temperature. This T at the bottom of this equation, it is written. So that means it is the constant term. Similarly, if I write for entropy, what will be the equation? dG by dt at constant pressure. This will be the equation for your entropy. Then, if I differentiate this equation, we have equation 13. This equation, if I differentiate this one, we will get this equation. That is del square G by del Ni into dP with constant temperature and number of moles. We have the chemical potential by pressure, and we have also volume by number of mole, that is VI bar. that is partial molar volume. Then again, this is another thermodynamic equation. Chemical potential at standard state equal to chemical potential at any state plus RT ln AI. AI is the coefficient, that is activity coefficient. Then it is again your mu W equal to mu W star plus RT ln A. These are the equations of a thermodynamic property, and you have to go through these things where thermodynamic applications are there. Okay, and lastly, we have this equation, that is pi equal to nRT or pi equal to CRT. So this is the final equation for the osmotic pressure, where pi is the osmotic pressure, C is the concentration of the solution, R is the universal gas constant, and T is the temperature in Kelvin. And this equation is very popularly known as Van 't Hoff equation. The scientist Van 't Hoff derive this equation. That's why it is Van 't Hoff equation. Then, and also one thing you have to remember, that osmotic pressure is a colligative property. That means the colligative properties are the properties which depends on the quantity of substance present, not the quality of substance. That means how much a substance is present, and it doesn't depend upon the what substance is present. If it is, let us, a solution containing 40 gram of sodium chloride, another solution containing, let us, 10 gram of magnesium sulfate. So the solution containing 40 gram of sodium chloride will have more colligative property than a solution containing 10 gram of magnesium sulfate. So this depends upon the amount or quantity of the substance present in a system, that is a colligative property. Then reverse osmosis process is just opposite of that osmosis, where movement of solvent particle from solution to solvent side, that is from higher concentration to lower concentration through a semi-permeable membrane. This is the reverse osmosis. This is also known as hyperfiltration. That is, this process is popularly used in seawater purification or in any water purifier. Then we have, that is water flux J equal to Q by AT. Q is the permeating solvent per water per time through membrane A, area A. Quantity of Q may be explained on weight basis. Just at the end we have R equal to 1 minus Cp by Cf, where Cp is the concentration in membrane permeated steam, and Cf is the feed inlet steam. So these type of equations are there. Then basic equation we have, JW is the solution diffusion mechanism. JW equal to DW, CW, VW. These are the things we have. I'm just okay. Lots of things are there. Actually, it is not possible to cover all the things in 1 hour of time for every unit. So I'm just telling you the basic things and the things we have needed for your theory examination. Concentration polarization we have. This is another concept. The concentration polarization results from the buildup of highly concentrated solute on the membrane surface as compared to bulk feed solution away from the membrane surface. This occurs because water formation at the membrane surface leaves the more concentrated solute layer, which must diffuse back into the bulk layer. So this is concentration polarization. That is, formation, water formation at the membrane surface leaves the more concentrated solute layer, which must diffuse back into the bulk layer. So this is your concentration polarization. Dialysis already discussed. Then you would have some equations like this. This is also highlighted in our PPT. Then electrodialysis. Then we have this is electrolysis through this delta. Then we have applications like desalination and water treatment. Then protein recovery. production of table salt, hemodialysis. This is the medical application of dialysis, that is transport or exchange or purification of water from a kidney disease. We have already mm, discussed this one. And selective membrane electrode, another another membrane type, that is ion selective membrane electrode, just like your dialysis process. We have equation from Nernst equation, E equal to 2.303 RT by NF log C by CS, and these are the membrane, its concentration range, and measure interferences. We have H plus, glass is the membrane, 10 to the minus 14 to 1 molar concentration, and none of the major interference are there, and these are the examples. Then we have specific gas probes are there, like your uh, like your polytetrafluoroethylene, polyethylene, polypropylene, nylon, cellophanes. These are some specific gas probes. Then detection analysis of particulate contamination. We have microfiltration membranes, ultrafiltration, nanofiltrations, and through microbiological analysis is also there, where you can detect some and pathogens like some bacteria, viruses separation from water sample or any other biological sample through microbiological analysis process. And at the end, the ultrafiltration is the preparation of plasma from the whole blood by removing particulates. So this ultrafiltration, it is a mechanism to prepare the plasma from the blood by removing the particulates. So these are the common things, and these are mm, uh, very much scientific things we have to remember. That is membrane separation processes. Then we have at the end, we have the last unit of our paper, that's electrophoresis. This is just an application of your you can say it is application of your electrolysis process, where the migration of the ions, that is cation or anion, to their respective electrodes through the application of electrolysis, application of electric field. We have these things. We have introduction, objective, electroosmotic flow, principle and operation, different forms of electrolysis, sub electrolysis, DNA gel electrophoresis. Sorry, this is electrophoresis. HTS page gel electrophoresis, two-dimensional, capillary electrophoresis, and capillary zone, capillary gel, capillary iso tachophoresis, capillary isoelectric focusing, capillary electrochromatography. Then at the end we have the summary. So before going through these things in detail, let's have a 3 to 5 minutes break now. So we will have some refreshment or tea at our respective homes. And after that, we will have the next unit, and at the end, we will discuss all the all the units we have learned from these last 7 days of class. And anyone having any question related to this paper or related to your program, we will discuss at the latter part of today's class. So let's have a 5 minute break. It is 18:43, so we will meet at 18:48. So till then, let's have some break. Welcome back, students, to this online platform of your theoretical class. And today we'll discuss your second paper of your PGDSC program of Block 5, the second paper, Block 5, containing two units, Unit 11 and Unit 12. And in the first part of today's class, we have already discussed the membrane separation processes in Unit 11. Let's have our last part of our paper of this block also, that is Unit 12, and it is related to your electrophoresis. Okay, so for electrophoresis, I have also prepared one. Uh, I have one mm, PPT for you. This is electrophoresis, and he is regarded as the father of electrophoresis, Arne Tiselius. And in electrophoresis, what happens generally, as we know, positively charged ion known as cation move towards cathode, while negatively charged ions known as anions move towards anode. So in our sample, the various positive and negative ions gets separated uh, by the migration to their respective ends, or we may say it is the electrodes. Thus, the charged particle can move towards respective electrode, and the direction is decided according to their charge. So, electrophoresis is a technique based on the migration of ion in an electric field. So, these are the contents. This is just it is a migration of charged particle of molecule in a medium under the influence of an applied electric field. So, here it is just remember this is the anodic end, positive end, cathodic end, negative end. So the positive charge is known as cations. So cation moves towards cathode, and these are known as anions. Anions move toward anode. So do not confuse between anode, cathode, cation, anion. Do not be confused. Just remember the cation is positive charge. It will migrate towards negative end, and that negative end is known as cation. Similarly, the negative charge is known as anion. The anion will migrate towards positive end, and this will named as anode. So this is just the migration of the ions to their respective electrodes based on their charge and applied electric field. So this migration depends on net charge of the molecule, size and shape of the particle, strength of electric field, property of supporting medium, temperature of operation, and at the end it is ionic strength of the buffer. And one thing you should know that the Arne Tiselius, the scientist that is father of electrophoresis, yeah, was from Sweden. He was Swedish chemist, and he awarded the Nobel Prize in the year 1948 for this valuable contribution. Then we have what should we expect if the macromolecules has a net charge q and we will apply electricity. What happen here? Here what happen? The electric field will be q into E, that is a charge into the electric potential difference. Then F equal to V into F, and where V is the value, the V is the volt, it is equal to QE by F. This is the equation. This is very much a simple basic equation for electricity. We can also define. We can also define ions electrophoretic mobility mu, that is V by E, it is equal to Q by F. And where electrophoretic mobility is defined as the rate of migration, that is centimeter per second per unit field strength, that is volt per centimeter. So we have mu equal to q by 6 pi Rn, where the terminologies are mu electrophoretic mobility, q is the net charge, it is small q, r is the ionic radius, n is the viscosity of the buffer solution, supposed to be happen. This is the effect of heat. Due to heat effect, there will be peak broadening, a resolution will be down, formation of temperature gradient or convection current resulting mixing of analytes and denaturation of enzyme and proteins. This is the effect of heat. If heat is applied, then as per Ohm's equation or Ohm's law, V equal to IR, then what happened? Uh, that means the H equal to I square R. So I will be increased. R is the in the opposite direction. This is the resistance, and this is the ampere in current, and that is current in ampere. So this will be migration rate will increase, and these things are there or not. Let's see in the PDF. So this is the electro-osmotic flow, that is a gas, that is the surface of silicate gas capillary which contain negatively charged functional group SiOH, and this overall solvent movement is called electro-osmotic flow. There will be movement of the solvent through the application of electric field in a sample is known as electro-osmotic flow. So this is the basic principle involved, and this is the operation. This is a gel electrophoresis where a gel is used here, and buffer with the which maintain the pH, and we have two ends, positive end and negative end. This is the anode and this is the cathode, with high voltage power supply. If we placed our sample, then the ions get separated uh, uh, to their respective electrodes through this applied electric field. So here what happened? Gel is used, and here the sample will be placed in. Different forms of electrophoresis: slab electrophoresis and capillary electrophoresis. And before that, we have one dimensional and two dimensional. Just to go through these things. And so in slab electrophoresis, separation are carried out in a thin flat slab of porous semi-solid gel containing an aqueous buffer. It is also a gel containing things, the semi-solid. In general, slab has dimensions of a few centimeter on a side and is capable of separating more than one sample. Then we have, if for example, we have a DNA gel electrophoresis, STS page gel electrophoresis, then two-dimensional STS page electrophoresis. Let's have the first one, DNA gel electrophoresis. So in this type, the DNA samples are run through agarose gel. In this gel, agarose gel, we have discussed in the ion exchange chromatography, I think, where agarose is used. With the help of a potential and differential mobility of DNA, the following instruments and reagents are important for preparing the DNA gel electrophoresis platform. We have gel casting tray. This is a tray where gel is casted, and this is just a U-shaped UV transparent plastic. Then we have combs. These are the plastic combs, uh, which are around which molten agarose is poured to form sample well in the gel. So in this tray or plastic tray, we will put the agarose, molten agarose, and with the help of this comb, this will make the surfaces plain. Once the gel is cast, comb is easily removed, and the well are made in gel slab. The size of the comb determines the volume of the well produced. Then electrophoresis buffer. This buffer is used triacetate EDTA. In short, it is TAE or triborate EDTA. So EDTA stands for your ethylene diamine tetraacetate ion, which is bonded to your three molecules of borate or three units of your acetate. Then, after preparation of the buffer, we have a loading buffer. One separate unit is there, which is used for the buffer container, used as the buffer container. This buffer is important not only for the loading of the sample in the well of the DNA gel, but also to impart color of the tracking of the sample. The components of the loading buffer are glycerol and dye. Glycerol helps to allow the sample to go into the sample well, and dye helps visualizing monitoring of the sample and extend the electrophoresis process. So here some dyes are used for coloration of the uh, visual for the visual monitoring, and we have glycerol which helps to allow the sample go into the sample well. So two types of things are used, that is the glycerol as well as the dye. So dye is for coloring, and glycerol is for um, help to allow the sample into the sample well. Then we have the next part, that is so this one, ethidium bromide. These things is used for the detection of DNA inside the gel. Ethidium bromide is a fluorescent dye giving fluorescence when intercalated inside the DNA and is used for staining nucleic acids. So ethidium bromide is carcinogenic and should be handled as a hazardous chemical, and one should use glove while handling it. So ethidium bromide, it is just a chemical required for your this is electrophoresis of DNA. Then we have trans illuminator. So these are UV light sources which are used to visualize ethidium bromide stained DNA gels. So we have just A and B. The A is your these are the slab electrophoresis separating DNA sample. Rectangles boxes are the well generated by the comb in agarose slabs. So these are the plates, like gel plates or gel slabs. And A and B represent gel slab before and after the run. This is the before and this is the after the run of your gel electrophoresis. Well M, it is a well M containing standard marker to examine the mass of DNA. So this is the process of your electrophoresis mechanism in DNA analysis. Then we have pulse field gel electrophoresis. So it allows investigator to separate much larger pieces of DNA than conventional agarose gel electrophoresis. In conventional gel, the current is applied in a single direction. However, in pulse field gel electrophoresis, that is PFGE, the direction of the current is altered at regular intervals. Yes, this is very much an interesting concept, that here the current is altered. That is anode and cathode gets altered, or AC or DC altered. So initially the agarose gel is prepared and sample are loaded into the well. After mixing it with the blue loading buffer, then the current is turned on and the direction of the current is changed in a regular pattern. This repeated until the loading die reaches near the end of the gel. The gel is then soaked in a solution containing ethidium bromide, which fluoresces orange when bound to DNA. So in this method, the current gets reversed at regular intervals. The current is altered at regular intervals till the dye reaches the end of the gel. So and at the end, by ethidium bromide, which have fluorescent property, will show orange color when bound to the DNA. We have STS, page gel electrophoresis. So in this technique, protein sample are run through page gel with the help of potential and differential mobility of different protein sample, which is responsible for their separation according to their mass of the protein. This is polyacrylamide gel are formed from the polymerization of the two components. That is your acrylamide and N-methylene bis acrylamide. So this is just two things. That is your STS STS page separation, and we have STS stands for your sodium dodecyl sulfate. Sodium dodecyl sulfate page electrophoresis. Okay, so uh, bis acrylamide is a cross-linking agent for the gel. The polymerization is initiated by the addition of ammonium persulfate along with either dimethyl aminopropionitrile (DMAP) or NNNN tetramethyl tetramethyl ethylene diamide, that is TEMD. So we have this structure of the polymer here, where different um, constituents gets interlinked to form a chain-like structure. And then we have this one, the schematic diagram of page gel electrophoresis, a typical page gel after uh, Gomez staining. We have the same process here. That is the buffer is at the bottom. Then we have one anode here, positive charge, cathode here, negative charge. This is the gel. This is the running gel we have, and this is the plastic frame. And when we put the sample that is with the gel, then the ions get separated based on their charges, and they will move to their respective electrodes. That is anion towards anode and cation towards cathode. Then we see a with the help of ethidinium, with the help of ethidinium, what is that one, ethidinium bromide. With the help of ethidinium bromide and some dye effect, we will have spots. That is the migration of the ions towards electrode. That means these ion moves towards bottom. That means these are the negative ions, and these ion move towards at the upper part where negative or cathode is there. That means these are the cations. So through this process, we will also have the electrophoresis mechanism. Then we have two-dimensional STS page gel electrophoresis. That is your two-dimensional sodium dodecyl sulfate page gel electrophoresis. Here, two-dimensional migration of the ions will be there. And as we have already discussed, the two-dimensional chromatography, where at one corner the sample is placed, and it with one definite solvent, then the same sample is turned to 90 degree, and this will again run with the second solvent. We have the separation of the constituent along horizontal and vertical axis or lines. Similarly, the same thing happen here, where there is two-dimensional, that is your amino acid has its own isoelectric point, that is pi. Pi is the pH at which the mobility of the amino acid is zero. Pi is the isoelectric point where the it is the pH at which the mobility or the migration or the conducting power of the ion is zero. Hence, protein which comprises amino acid do have a characteristic pi value, that is the isoelectric point value. In 2D gel electrophoresis, proteins are separated according to their pi value, which allow to mix with STS. So denaturated protein are then allowed to enter, are then allowed to enter a polyacrylamide gel. The passage of protein by potential ultimately separate the protein according to their masses. So depending upon their masses here, and depending upon the isoelectric point, uh, the separation occur. Then we have capillary electrophoresis, and this is just a figure of your capillary electrophoresis, where these are the buffer solution, where these are the buffer solutions, and we have the current or supply of electricity here at the two ends, and this is the anodic part and this is the cathodic part, and always and there is one detector here. This is acts as just like a salt breeze in the galvanic cell, and this is the gel. Sorry, this is the sample container, or here, or this is the capillary here. This method is capillary electrophoresis. So this is the capillary here, which contain the sample, and when this process is started, what happened? The respective electrodes will move towards their respective ions will move towards their respective electrodes through this application of this electric field. Then sample introduction is there, that the electrokinetic injection or pressure injection. Then we have detection, just sample injection and detection. There are two main activities in this separation method. Then capillary zone electrophoresis, also known as free solution capillary electrophoresis, and it is the simplest form of capillary electrophoresis. It is used to separate ion species by their charge and frictional forces. The separation mechanism based on difference in charge to mass ratio. Okay, then we have capillary gel electrophoresis. Here, in capillary tube, the gel is used to have the sample with it, and it again depend upon the porous gel polymer matrix, where the sample is entrapped, and this will be again the same process is carried out, that is a capillary electrophoresis mechanism. And the gel in electrophoresis which are commonly used, these are polyacrylamide polymer formed by the polymerization of acrylamide CH2 in presence of cross-linking agents. The pore size of the polymer depend upon the ratio of the monomer. And then we have a capillary isotachophoresis. This is just focusing technique based on the migration of the sample component between leading and terminating electrolytes. Solutes having mobilities intermediate to those of the leading and terminating electrolytes stack into sharp focused zone. Although it is used as a mode of separation, transient ITP, that is isotachophoresis, has used primarily as a sample concentration technique. So this is just based on the migration of the sample component towards leading and terminating electrolytes. That means it is the starting point and the end point. Then capillary isoelectric focusing CIEF. This technique is allow amphoteric molecules. That is, with amphoteric means it with having both characteristics of positive, that is cation and anion, such as protein, to be separated by electrophoresis in pH gradient generated between the cathode and anode. A solute will migrate to a point where its net charge is zero. At the solute isoelectric point Pi, where migration stops, the sample is focused into a tight zone. In CIEF, once a solute has focused at its Pi, the zone is mobilized past the detector by either pressure or chemical means. This technique is commonly employed in protein characterization as a mechanism to determine protein's isoelectric point. That means, in general, samples where the isoelectric point, or at isoelectric point, there will be no migration of the ions at a definite pH. But in CIEF, capillary isoelectric focusing, we will exercise some external pressure or chemical means, uh, to for the movement of the particles towards the respective electrodes even at isoelectric point. So this mechanism or process is carried out to determine the isoelectric point of protein. Capillary electrochromatography. It is another method, that is electrochromatography method using your capillary. This is CEC, that coupled with high separation efficiency of CZE with HPLC, that is uses an electric field other than hydraulic pressure to propel the mobile phase. Then we have in early 1980s we have packed column and micellar electrokinetic capillary concept are there. Then capillary electrochromatography appears to offer several advantages over other techniques like HPLC. It is capable of separating of uncharged species. Then we have the second thing, it provides highly efficient separation of micro volume of the sample solution without the need for a high pressure pumping. In electrochromatography, a mobile phase is transported through a stationary phase by electroosmotic flow pumping rather than by mechanical pumping, thus simplifying the system significantly. In addition, electroosmotic pumping leads to the plug flow profile rather than the hydrodynamic profile. And at the end, we have the flat face of plug flow leads to less band broadening than the polyhydrodynamic profile. This results in greater separation efficiency. So uh, you have to uh, remember many things in this unit of membrane separation as well as electromigration, that is electrophoresis. Just I have gave you a uh, broad idea or basic things about these techniques, but these CGE, CHE, CISF, CIEF, CITF, TP, these things you have to remember what type of molecules gets separated by what means, where there is gel is used, where there is polymer is used, where there is application of isoelectric point is there, where amphoteric substances are separated through which mechanism. And these are the figures you have to uh, mm, practice these things or figure. And at the end we have 10 to 15 minutes left for some discussion of this paper, and hope we are able to touch every aspect of your second paper of your PGDSC program. And actually lots of things are there in a single unit, and IGNO course is so vast that it cannot be cover up within 1 hour of time. Okay, so I intentionally I have skip some of the portion of your unit which might not come in your theoretical examination, and related to today's discussion or anything else from our last 6 days. And that is, we have discussed from your separation methods to solvent extraction, different chromatographic methods, followed by today's, that is separation through membrane, as well as the electromigration, that is electrophoresis is there. So it is over to you, students. And mm, as you all know, my laptop is not responding your voices. So I request you all to put your questions or any other query in the chat box, and I will mm, uh, try to give you the answer. So it is over to you. And And I think all these papers you have 100 marks, and you will face 20 into 5 or 10 into 10, 10 questions. So here was the first question. How does separation of eggs occur in facilitated diffusion transport after passing through membrane? I just forget that method. Facilitated diffusion transport after passing through the membrane. Just wait. Actually, in facilitated diffusion transport method, what happen? The sample gets diffused. Let us, if it is surface transport, then what happen? Now, the on the surface of the membrane, the gaseous samples are adsorbed, and after passing through that membrane, what happen? The gaseous molecules get separated on the basis of their interaction with the surface. And here what happened? The sample gets diffused with the in the sample chamber, sample chamber, and after that, with some external pressure or any chemical reaction, the constituents gets separated through the membrane, and this will be the separation after diffusion, that is facilitated diffusion. So this is diffusion followed by separation through membrane, and this the transport occur due to some pressure, external pressure applied, or some chemical reaction. What is Cephadex gel and its IPM feature? Okay, Cephadex gel. Oh, we have discussed this thing yesterday actually. Cephadex. Just wait. I have to look for that. I think it is ion exchange. Just wait. I have to search because I do not remember all these things. Yes, dextran. Then we have polyacrylamide, agarose. We discussed today. It is solvent selection, mobile page. No, we have Cepatex in which unit? Just hold. So, Chandni, it is from which unit? Cepatex? Chandni Sahu. So let's have our internet. It is what is Cepatex gel and its IPM feature. Let's have some browsing here. Cepatex gel. Yes, this is a version of your dextran gel. This is the dextran gel, that is the linkage of cellulose moieties, and this is used for gel filtration, and it is 20 to 300 micromolar. It is the bead size, and its types are like this. It is just G10, G15, G25, all these are there. with your globular protein and dextrans are here. They're all actually biological terminologies. So just remember the Sephadex resin. This is generally named as Sephadex LH20, which is used for the separation and purification of organic molecule such as steroid, terpenoids, etc. So this is your Sephadex resin. Okay, okay, okay. So okay, okay. This is assignment question. Okay. So but you will have this one in block 4. I think it is there. In block 4, you have size exclusion chromatography. In that, you will have this dextran. This here it is written Sephadex. Soft gel dextran. Its trade name is I think Sephadex, and you have these things are there. Sephadex. Okay. Then the next question will be, this is just a gel. What is the vacuum pressure range in pre-vaporization for separation of azeotrophs? Azeotrophs means your solutions with same boiling point. Azeotrophs. So in per vaporization, we have discussed today this concept, that is per vaporization concept. Uh, it is in our previous unit, unit 12. Sorry, unit 11 is this one, previous one. Per vaporization, this is this one, pre vaporization. We have, just wait, we have to see. This is the pre vaporization, where two types of mixtures are there with same boiling point. Let's see, let us have the mixture is azeotropic mixture. Then membrane separates liquid feed and vapor permeates phases. So, in case of azeotropic mixture, also the same principle of per vaporization vaporation applies. That the components of the liquid feed phase vaporizes and permeates through the membrane, and the separation involve a phase change. Okay, this phase vaporization, that means the constituent change their phase from liquid to vapor and then permeates through the membrane. And if the vaporization methods separation of polar and non-polar liquid mixture, and the driving force for this kind of separation is partial pressure difference of the permeating component across the membrane. The gaseous permeate is usually held at low pressure, and liquid feed stream is at the elevated temperature to facilitate evaporation of permeating components. Evaporation is an attractive process for separation of liquids which form azeotrophs. Here it is written, that is where vapor and liquid have the same composition in equilibrium, and the standard distillation cannot achieve the separation. So per vaporation, there is separation of the liquid mixture from your azeotrophs with the same boiling point. So in per vaporation, what happened? The separation of polar and non-polar liquid mixtures are there. So depending upon the phase change of the components from liquid to vapor, if the boiling point is same, that means the phase change will be simultaneous. So when the phase change occur, they will diffuse to this membrane differently depending upon their components. As their boiling point is same, not mean that their components are same. If two components A and B is there, A with boiling point let us 200 degree centigrade, B is boiling point A, the same 200 degree centigrade, they will form the azeotrope mixture. And this is not mean that they have the same component. They might get vaporized from liquid to vapor at 200 degree centigrade, but after diffusion, their interaction with this membrane and their permeability through this membrane might be different. So this will separate the components of the azeotropic mixture. Okay, and I think this will be the answer for this question. So the boiling point is same, but the components may or may not be same. Can gel electrolyzer can be used for RNA? But it is not written here, but it might be applicable to RNA also or Rajasmita Misa. This is might be applicable. I think these are all biochemistry related things are there, but you have to remember the applications of your electrophoresis, and I think if it is applicable to DNA, and it might be applicable to RNA. Anything else? Okay. So if no questions are there, so the time is also we are also at the end of our end of this paper. And Ojas, you put were nice questions, and thank you for that. And I also thankful to all of you students for your patience hearing or patient listening to my presentation of your different on your different topics. And today we completed or we covered all the units of your paper 2, and this is our schedule. Just see this one. This is our schedule. So on 7th of August, you will be, it will be Rajesh Kumar Sahu. Dr. Rajesh Kumar Sahu will take your paper, the first paper, MCH-1 paper. This is related to your as basic analytical chemistry part. This is paper 1. And his class will be ended by 16th of August, that is after Independence Day. Then uh, then the day after that we have the last part, that is your electroanalytical techniques. And these are very much interesting topics that is related to your electrochemistry and its application. With that we have studied in class 12 or in degree level. So hopefully you will stay safe, stay happily, and best wishes. And we will meet again at 17th of October, sir, August. And thank you to all.
Thank you, sir.
And also I will share all the PPTs in your WhatsApp group. So do not bother about that, and just go through your PDFs, and you should see the last 2 to 4 years question of your respective papers, and mostly from that previous year questions, the questions are repeated, might be repeated for today's this year theoretical exam. So thank you again. So
Thank you,
God
sir.
bless you all.
Thank you.
Abrar, your voice is not audible to me. As you know, my laptop has some problem. So you may put your question or anything else you want to say in the chat box. Please. Abrar. Okay. So thank you to all.